Thanks, mate. I know it's lunchtime, so thanks so much for sticking around. I'm Bing Chun Wang from the National University of Singapore, and today I'll be presenting our work on optimal contract design for collaborative machine learning. Okay, sorry. Sweet. All right. So I want to start the talk with an excerpt from a conversation between the AI luminaries Pippi Lee and Jeff Hinton. In it, Pippi said, not a single university in the US back then can train a GPT in terms of compute power. And even combining the resources from all universities in the US still cannot train a ChatGPT. I know a lot has changed since the interview, and especially with the recent news on DeepSeek. The power imbalance in AI development remains a critical issue even today. And public investment, as suggested by the luminaries, provides one way to address this problem, but it often comes with other forms of inefficiencies. So in this paper, we actually asked the question, can we actually design mechanisms to democratize AI? And to this end, collaborative machine learning sounds like a promising crowdsourcing paradigm. Through collaboration, small parties can join their limited resources and then collectively train a good performing model in return, which would not be obtainable at an individual level. Despite the optimism, and except for a few successful cases in the public sector, in reality, the idea itself hasn't quite taken off yet. So that leads us to ask the question, why it is the case. If we put our economist hat on and delve deeper into the incentives underlying a typical CML scheme, it wouldn't be hard to realize that the vanilla version of CML assumes an unrealistic level of altruism. And to see the point, we can start by making this observation or assumption that more resource contribution increases model performance. So from a collective standpoint, parties should be incentivized or motivated to contribute as much as possible so as to maximize the model's accuracy. But on the other hand, we also know that contribution isn't free. It costs money in the party's end in terms of data, compute, or maintenance. So privately, a rent-seeking party might instead optimize their net profit by lowering the contribution to below the socially optimal amount. And this clear conflict of interest seems to impair the performance of CML schemes. The problem, however, runs even deeper. As was shown by Karimi Reddy, Gore, and Jordan in their 2022 paper, we only need to add this additional heterogeneous contribution cost assumption to arrive at a depressing equilibrium where all parties but one contributes. So instead of having a prosperous collaboration, we end up in a failed system. And this problem, despite sounding egregious, can actually be solved elegantly with the design of contract. As we can see here, if indeed the participants' contribution costs are public information, we can still ask the coordinator to assign the best performing models to all parties, but require them to contribute different levels or different amounts of resources based on their contribution costs. So in other words, we can effectively write the contribution costs into our contracts. But the situation starts to get more interesting once we move away from the cost visibility. In reality, for instance, firms could be procuring GPUs from private vendors, or they might be recruiting data labelers subject to different wage requirements. And because these processes are often happening behind the doors, it would be very hard for other parties to verify the actual contribution costs. And with private costs, we can see that the previous strategy apparently breaks down because parties now can misreport their contribution costs in order to gain a better deal. And in economic terms, this is what we call a principal agent problem, or more specifically, a monopolistic screening problem. Although the idea itself comes from economics, contract design with model rewards poses unique challenges. We know that, first of all, models, unlike money, are non-rivalrous, which means that a party's use of the model does not affect other parties from using the same model. And because models can be replicated almost free of charge, this creates a very different budgetary dynamic from the monetary payments. And then the second challenge arises from timing, because we know that contract design happens prior to resource contribution and model training. Yet a model's realized accuracy is only known after it has been trained. So this means that assigning deterministic model rewards no longer works because that would risk insolvency or underutilization of the model budget. And to this end, our work is among the first few to introduce optimal contract design with model rewards into the collaborative machine learning setting. So now let me propose a complete timeline for a CML scheme with optimal contract design. So in the first step, the coordinator, upon incorporating the background knowledge of the private cost types, published a contract manual with different reward contribution options, one designed for each party type. And then in the second stage, this manual is presented to the participants who can then choose to sign it by selecting the option in their best interest. And finally, during the collaborative machine learning stage, the parties who have signed the contract contribute the promised resources. And then the coordinator can then use these resources to train the model on the party's behalf. At this stage, the realized accuracy of the model is known. So based on this information, the coordinator can then prepare the model rewards and offer them back to the participants. Having set up the structure of the incentive mechanism, we can now shift our focus to solving for the optimal contract. So here I'm going to denote a party by their private cost type. So a party with per unit cost CI makes contribution MI and receives model reward RI. As was mentioned before, a party aims to maximize its net profit. So its utility function takes the form of the expected revenue from the model rewards less the total contribution cost. On the other hand, we have the scheme coordinator who represents the collective interests of all parties in a CML scheme, and whose utility function is represented by the expected accuracy of the collectively trained model. As we can see here, we also have encoded the information assumption in the expectation operators. So the coordinator here only knows the probability distribution of the private cost types, which we assume to be multinomial in our setup, whereas a party knows their contribution cost and that they will be contributing when joining the scheme. So they have a slight information advantage. And with that, we can now formalize the optimal contract design as a constraint optimization problem. The goal is to maximize the jointly trained model's expected accuracy subject to a bunch of constraints. And we can see here the first type of constraint is what we call the individual rationality constraint. So in words, it basically means a party upon joining the scheme should expect a weekly higher net profit than they would by opting out. So here we use FI to denote the opportunity cost or reservation utility obtained by a party of type I, and assume it to be the net profit gained by the party if they train the model independently. Next, we have the incentive compatibility constraints, which basically requires a party should receive the highest net profit by choosing the option designed for their type. And by enforcing incentive compatibility, we essentially ensure that parties are truth-telling when joining the scheme. And this in turn guarantees the validity of the contract design. And lastly, we have the model budget constraint, which mandates that the assigned model rewards must never surpass the collectively trained model in accuracy. And it should be noted that here to guarantee sovereignty, this budget constraint is specific to every realization of the type distribution. So consequently, we have a combinatorial number of scenario oops to consider, and this makes the problem very hard to solve. In the paper, we actually come up with a strategy to solve this problem. And the rough idea is to actually relax the original problem through constraint relaxation into a simpler form, which we call the first moment problem. And the first moment problem is nice in the sense of having fewer variables to operate with and also fewer constraints. But more importantly, it is convex, so we can resort to classical numerical optimization algorithms to efficiently find a solution. And after solving this first moment problem, we can then use a mapping technique to recover a solution for the original problem. And if you're interested in theoretical design, theoretical analysis, in the paper, we have also conducted constraint analysis and demonstrate the properties that an optimal contract should satisfy in theory. But here I would spare the audience with the technical details, but you can find the full derivations in the paper. Okay, so to understand the impact of a CML scheme with optimal contract design, let's now turn our focus to the experiment results. So here we categorize possible applications into three distinct scenarios based on the contribution cost of the parties in the collaboration. So here the small red circle represents parties or big firms who have low contribution costs and would train the model independently. Whereas the large yellow circle represents smaller parties who face exorbitant training costs and would not train the model independently if the task is left to themselves. And we also consider this intersection area where there is a blend of big firms and small parties in collaboration. In the big firm cooperation scenario, as we can see that all parties have initial incentives to train the model. And here we organize parties by decreasing per unit contribution cost. So a type 5 party has the lowest per unit contribution cost and would utilize the largest amount of resources for independent model training. With collaborative machine learning and optimal contract design, we can see that parties now all get better performing models, and most parties would contribute more than their reservation levels. However, interestingly, we also find that a party might be incentivized to contribute less. This is actually a direct consequence of the incentive compatibility constraint. So in other words, had we asked party of type 5 to contribute more than their reservation level, this would efficiently cause them to deviate to choosing the contract option designed for a type 4 party. So this incentivized reduction is key to guarantee the validity of the contract design. And next, we have the small party teamwork scenario. As we can see here, without collaboration and incentives, parties wouldn't train the model due to exorbitant contribution costs. But with collaborative machine learning and optimal contract design, they can now successfully overcome the model training barrier and get good performing models in return. And in addition, we can also see that the model rewards they get are proportional to the data contributions they make, which demonstrates fairness in the process. And lastly, we have perhaps the most interesting case where there is a collaboration between big firms and small parties. So here, 3 out of the 5 types are willing to train the model independently, whereas the other 2 are facing exorbitant training costs. With collaborative machine learning and optimal contract design, again, parties now all get better performing models, but more importantly, despite the presence of dominant players, smaller parties like type 1 and type 2 can still benefit from collaboration by even making a modest amount of contributions. So this highlights the trickle-down effect of the incentive mechanism. I want to end this talk with a quote from a book I'm reading at the moment. James Clear, the author of Atomic Habits, writes, "You do not rise to the level of your goals, you fall to the level of your systems." And I think this insight befits collaborative machine learning really well. Simply aspiring to collaboration, however noble that may be, is not enough to guarantee good results. As we have seen earlier on in this talk, when parties are rent-seeking and self-interested, they can engage in strategic behaviors that undermine collaboration and lead to failures. And to address this problem, we can actually design contracts that attend to the conflict of interest and information asymmetry, and efficiently align the private interest with the public goal. So together, collaborative machine learning and optimal contract design offers a viable approach to think about the democratization of AI development. Well, a lot of work still remains to be done. We hope that our work provides a stepping stone for the future works to come. Yeah, thanks. Yes, please. No, unfortunately not. Yes, but I think because so the thing is, if after we simplify the problem into the sort of first moment format, we can actually use the numerical optimization algorithms to efficiently find a solution. I think the closed form would be a good thing to do, but it would be very hard in this case because of especially the expectation operators. Yeah. Oh, sure. You can actually find a section in which we detail the constraint analysis. So roughly speaking, we have the sort of we can actually reduce the incentive compatibility constraints to a much smaller set, in which I think it's the adjacent adjacent type constraint that is binding, and also we have proof that the lowest type should receive the reservation utility. And the highest type should be given the best performing model. So that result kind of aligns with some of the desiderata proposed in say, cooperative game theory. Yeah. Yeah. Any other questions? Okay. The what? The affine function. Oh. Oh, F5 function. So actually, if you check the paper, we define it as the optimal, the net profit gained by the party if they do the sort of model training independently. So essentially, we're using the same framework, but instead giving party the power to optimize by themselves. So that's actually defined by the solution of another optimization problem. Yeah, and the details can be found in the paper. Yeah. Okay. And if you have any like other questions or insights, feel free to find me in the poster hall. Yeah. I have just one last Yeah, sure. In this case, like the number of people there is fixed, right? So let's say like I'm encouraged by your design and I want to buy. So if you have now increasing or decreasing number of people and you want to update your contract. Sure. Sure. So I think that relates to the problem of scalability, right? We actually run some like preliminary experiments showing that the number of participants is not like a huge thing when it comes to scalability, but the actual challenge is with the increase in the number of types. So here, I think at the moment, this framework seems to be the best for cross-silo settings where you have like a limited number of private cost types. But if you want to like increase the number of cost types, you probably have to look at the last future research direction and think about the relaxation of the distribution assumption. Yeah. All right. Thank you so much.